Hello, so today we're going to be talking about the history of atomic structure. Before we dive really into what atomic structure is and what it's all about in the realm of chemistry, it's always best to have a little bit of background on the material. So the way we're going to kind of evaluate this, we're going to do a little brief overview of what and how atomic structure evolved throughout the years, hundreds and thousands of years of thinking, and so on and so forth. So the practical and theoretical foundations for atomic structure has progressed for thousands of years, like I said, through the effort of many scientists and philosophers, including Democritus, John Dalton, J.J. Thomson, Robert Millikan, Ernest Rutherford, Niels Bohr, Erwin Schrödinger, and Werner Heisenberg. So we're going to kind of do a brief overview of all these scientists and their contributions in relation to atomic structure. You will be responsible to kind of know some of their background and as well as what they postulated for tests and quizzes and stuff like that. So feel free to take notes as we go along. So first one is Democritus, this goofy looking guy right here. He was born and lived in Greece around 400 BC. So this is thousands of years ago in regards to this. So, atomic structure was talked about during the time. He was what's called a philosopher. So there wasn't really any definitive scientists at the time. Philosophers really focused on religion and mathematics and everything like that, stuff that could be proven. But the thing is, if you couldn't prove it, you were typically considered, cuckoo, which in ancient Greece could lead you to be exiled from the city and from the state and so on and so forth. So it was kind of a big thing to kind of come out with your own ideas, especially if it didn't support the religion that you were in or had support from your fellow philosophers at the time. He was the first one to use the term atom in his documentation that historians have found. He argued that matter was composed of tiny indivisible particles, which turns out to be atoms. Believed that atoms were indestructible, indivisible, and were constantly in motion without rest. So he thought that atoms always moved. They never stopped at all, which is kind of true. Not necessarily, but it is kind of true. His ideas were lost for centuries due to the debate between Aristotle, to where Aristotle did not agree with that atoms existed. Aristotle, during his time, was the biggest philosopher or scientist at the time that everybody went along with. So if anybody disagreed with Aristotle, nobody really agreed with that scientist or philosopher at all. So Aristotle kind of put him on the back burner for a long time, and a lot of his stuff wasn't even really developed until hundreds of years later. Then we get to John Dalton, this classy young fellow right here. He was a British scientist during the 1800s, so very large leap from 400 BC to 1800s. So, for a lot of the stuff in science, it didn't really start developing until it was culturally good to start having ideas of your own that went against, church and state and so on and so forth. He reestablished Democritus' theory of atoms. So he reestablished it in the more modern sense, and he was able to develop further on that idea. He established a universally accepted atomic theory of matter, which has four main postulates. The first one is each element is composed of minuscule particles called atoms. So again, I'm developing further on Democritus' theories. He stated that all atoms of a given element are identical but differ from one another. So an atom of calcium is different from an atom of magnesium, but the atom of calcium will always be the same for each atom of calcium, is pretty much what that's saying. Atoms are neither created nor destroyed by any chemical reaction, so this follows the law of conservation of massive energy that we talked about last unit. But he was the one that really kind of formally put it into chemistry terms, I guess is the best way to say it. A given compound always has the same relative number and kinds of atoms. So again, that goes back to the law of definite composition, where that was really developed in regards to that. So CO2 is always CO2, H2O is always H2O, CO2 is always going to be carbon dioxide, H2O is always going to be water. So in regards to this, again, H2O is always going to be water. Hydrogen peroxide, even though it has a similar molecular formula as H2O, does not mean it is water. So it's called hydrogen peroxide. So it's an entirely different thing, has different physical and chemical properties. Same thing with carbon dioxide. So J.J. Thomson, this is where we start getting a little bit more intricate. He was also a British scientist. He identified the electron, not necessarily he discovered it. So he knew it was there, but he didn't know exactly what it is. So he kind of postulated there was something there at the time, but he didn't have enough technology or advanced techniques at the time to really identify that electron itself. It was the first known subatomic particle that we were able to identify within an atom. He demonstrated that atoms were not indivisible and had a substructure. So you can split an atom. You can tear it apart into separate protons, neutrons, electrons, so on and so forth. And we've learned even modernly you can start taking those subatomic particles and start breaking them down even further into quarks and stuff like that. He created what's called the plum pudding model of an atom. It demonstrated that negative charges, which were the electrons at the time, were evenly distributed. Evenly distributed in an atom's positively charged interior. So this is pretty much what it looked like. He saw that the majority of the atom was positively charged, but there was these little electric negatively charged particles floating around there, and he was able to distinguish that there was a difference in charge, but he was not able to distinguish mass at the time, which is the reason why he was not able to identify the electron for what it was. But he did see that there was a difference in charges, allowing those to cohesively come together as an atom. Robert Millikan is where he starts kind of stepping it up a little bit. He was an American scientist. He experimented with charged oil drops in electric fields. So the way this works is that he sprayed oil into this kind of contained area, and he put an electric field between two pieces of metal. And it was a uniform electric field. And what he saw is that as he sprayed oil into it, particles would shift depending on their charge. And he was able to observe this through a microscope. So based off of that, he was able to determine the charge and mass of an electron. This is partially due to the fact that the charge that he put into the metal wire, if the electron went a certain magnitude away from it, he could distinguish the charge of that electron and also the momentum of it too. And with momentum, if he knows the speed, then he can also know the mass. So that's how he was able to determine the mass of an electron. So it turns out the charge of an electron is a really low number. It's 1.6, all those numbers, times 10 to the negative 19th coulombs. Coulombs are used in units of charge. And then the mass of an electron is 9.1, all those numbers, times 10 to the negative 31st kilograms. So that's ridiculously small too. Ernest Rutherford, he performed the famous gold foil experiment, which you may already know about from your previous science classes. But he developed a theory that each atom has a central positive nucleus surrounded by negatively charged orbiting electrons. So the main thing was that he proposed that there was a majority of the atom's mass was within the nucleus. And this is what made the gold foil experiment so cool. The way he set it up was they set up a little laser that would shoot particles at this gold foil. And he told himself that he set up a circular not reflector, but refraction fluorescent screen that could catch any incoming particles. And what he noticed is that when he shot particles out of the laser into the gold foil, they would bounce off in all different directions depending on where they were going. Some of them would go straight through, and some of them would actually bounce off of something and hit something. So he knew that there was a mass there. However, the thing is that if the mass was large enough, it would just bounce all the time and hit right back towards the laser. He found that some were actually going through, so there was open space within that gold foil, even though it looked like it was a solid material. So he was able to identify the nucleus was in the center of an atom, and that it contained a majority of the mass, and that when he shot particles through, all the open space around the nucleus that was the electron cloud, particles could pass just right through it. So he was really able to identify, the relative location of these subatomic particles. Niels Bohr is where it starts getting really, really interesting in regards to applications of chemical subjects and chemistry itself. He was a student of both J.J. Thomson and Ernest Rutherford. So this is, somebody that was a protege of two famous scientists that I think some of them actually won Nobel Prizes in. He developed further on Rutherford's model of the atom by application of what's called quantum theory. He created what's called the planetary model of the atom. It's also referred to as the Bohr model. You'll hear me say Bohr model a lot more than planetary model, so just be aware that both of them mean the same thing. In this model, the electrons circle the nucleus in a defined rigid orbit. And what that really means is mathematically they distinguished that there was no variation. They were always in the same round orbit. The orbit distance was also analogous to the energy level of each electron. So what he said was that the nucleus, based off Rutherford, is right in the middle where a majority of the mass is. But the electrons are on the outside because with this positive charge of the nucleus, there has to be negative charge kind of keeping it together, being attracted to it. But he knows that not all the electrons can be all in the exact same place. So he said, well, what if the electrons were, since they have mass, they can be exposed to different energies because clearly they can travel at different speeds. So he said, okay, what if I set them up into a planetary model similar to Copernicus's planetary model of the planets? He said, okay, let's say the nucleus was like the sun, okay, and then this is Earth, and it would spin around a certain orbit, but there's a certain distance due to a force of gravity, or in this case, a distance due to the energy of an electron. And so he set up these energy levels to create this planetary model. And for the most part, it's pretty accurate in regards to when you can start doing applications of basic chemistry. When you start getting to more advanced chemistry and physical topics, you have to use a higher level model that we'll dive into here in just a second. Erwin Schrödinger, which you've actually probably heard of a little bit before if you watch like Big Bang Theory and stuff like that, he was an Austrian scientist. He contributed to the wave theory of matter and added the fundamentals of quantum mechanics. So Einstein had predicted that there was a duality of particles, both wave and particle form, depending on how you observe them. And so what he did is that he took this theory and he applied Niels Bohr's quantum mechanics of an atom. It was able to develop calculate the amount of energy each orbiting electron had. And so by calculating this, he was able to explicitly be able to excite electrons from one state to another. And so with this, we could actually distinguishedly determine how much energy it takes to shift those electrons in ways that we really want them to. But he also created an analogy for electron duality, which electron duality, since it is a particle, it acts similar to what Einstein predict for light, particle wave. An electron can act as both a particle and a wave, but in doing so, since it is within an atom, he had to create this analogy that would kind of come across a little bit better. So he came up with the idea of Schrödinger's cat, and what it is that it pretty much states if he placed a live cat inside a box, okay, and as soon as he closed that box, this mechanism that was attached to the box would either snap and break a vial that would fill the box with poisonous gas and kill the cat, or it wouldn't. So he stated that until you observe the cat itself, you can think of both the cat as dead and alive. So in regards to duality of electrons, he was saying that you can both think of the electron as both a particle and a wave, depending on how you observe it. It has a mass, has a velocity, which means you can, see it as a physical form. But the thing is that when you look at it once, it may be there, and when you look at it twice, the second time, it may not be there because of how it's a wave. And we'll dive further into that here in just a second. But again, it demonstrates the uncertainty and probability of the location of electrons at any given time within an atom. So if it was if you look at it as a wave has multiple crests. So if you think of that, those crests as particular locations, if an electron has 3 crests in a wave function, then it can be in 3 different places at one time. So that's what he was trying to come across that. It's a little bit more advanced, but that's what he was shooting for. We'll kind of go further that in class if we need to. Werner Heisenberg is where it starts getting really cool. He was a German scientist. He was famous for debating against Erwin Schrödinger. So they actually debated a lot within the scientific community because they both were alive and very prominent in their fields at the time. So they kind of played off of each other a little bit, but they both led to very significant discoveries in the realm of physics and chemistry. He helped define the modern quantum mechanics. And what he did was he created something called the uncertainty principle. It states that one can determine the momentum and the position of an electron within an atom, but not at the same time. The way I try to provide an analogy for you is a running person, somebody that's running. If you take a photo of that person, okay, and take a still shot, you can tell where that person is at one particular time based off that photo. But you cannot use the photo to determine how fast they are going. But if you were to set a sensor up and let the person pass through it, you could determine the momentum and how fast that person is going. But you cannot determine what their position was, because if they were moving at the speed of light, it would seem that they're moving in all positions at once. So he said that you can determine either the position and momentum at one time, but you cannot determine both at the same time. So that's what the uncertainty principle is. It can be further demonstrated by, again, like the runner photo analogy that I just told you about. All right, so that's it for that. It's kind of basic stuff, but very important in regards to how to think about the quantum mechanical model that we'll dive further into in this unit, as well as how the atomic structure of an atom progressed throughout the years that science either didn't exist at the time or existed as philosophy up to modern science now, and how we really think about things. But it's important to know where these roots are. So if you have any questions, please come talk to me. Email me, anything you need to. Otherwise, I will see you in the next video, and I hope to see you in class. Bye.